All right, let's review some of the properties of rational exponents here. First of all, much of this should be review. We know that when we multiply two variables to various powers or various exponents that we're going to add the exponents 2 plus 3, or this is equal to x to the fifth power. We hope that's basic and we hope you understand that. The next one would be when you have something in parentheses raised to a power, that's when you would multiply those two exponents. This one would be 2 times 3, or actually x to the sixth. We hope you see that too. Now, one thing you have to be careful of is, especially with all the work we've done in quadratics, when you have a quantity that is squared that contains both a constant or a number and a variable like an x or an a or an m or an n, you have to square them both. So this is really 3 squared times x squared, or a simpler way of saying it would simply be 9x squared. All too often, I've seen students who will do this and they'll just go, oh yeah, 3x squared, and then they just go 3x squared. They forget to square the number as well. That is not right. You got to square the number as well. Don't forget this 2 here. Okay, so this is not right. 9x squared is correct. All right, x to the minus n is equal to 1 over x to the n. Just bring, whenever you see a negative exponent, bring it down to the bottom and make it positive without changing the variable itself. Just change the sign of the variable. And conversely, if you had something like 1 over x to the negative n here, when you bring it up top, you simply change the sign as well. So this would be x to the n. Okay, so if you have x to the n on the top, take it to the bottom and change the sign. There's a plus right there if you don't see it. Okay, if it was in the bottom and it's negative, you can bring it up top and just make it a positive. All right, hope that helps there. X to the fifth divided by x to the 2, just like we added the exponents themselves up here. Now when they're divided, one's on top, one's on bottom, you subtract the exponents. Okay, so you do x to the third in this case. All right, I'm going to go to another page and let's do some examples of how some of these things work. Okay, when you see square root of 50, all right, because the roots work very similar to exponents in this sense. And so what I'm going to do here is I'm going to try to divide this up into two things and look for a perfect square root. We know that 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Oh, wait a minute. Isn't that 2 times 25, or 2 times 5 squared? Because whenever I have something squared under a square root sign, it just comes out. The 5 comes out, no longer is it squared, and the square root of 2, that's all that's left. Once this comes out as a 5, that's 5 square root of 2. Done. So look for perfect squares when you see big numbers like this. If you want to check it on your calculator, you can take the square root of 2, multiply it by 5, and you should get a decimal number. And you get the same thing if you just punch in 50 and take the square root. But we want you to know how to manipulate these square roots and get them in terms with or without a calculator. Okay, next one down here, I have the fourth root of 8 and the fourth root of 2. So I'm looking for something under there that would be multiplied 4 times, and then I could pull it out and leave behind something else. The fourth root of x to the fourth would be just x. Right? This is x to the fourth. It's x multiplied by itself 4 times. So what I'm looking for over here is I'm looking for something that might have 4 2's in it, 4 3's in it, 4 x's in it, whatever. There's no x's here, but I do know that 8 is 2 to the third, or 2 times 2 times 2. So I can rewrite this as the fourth root of 2 times 2 times 2. That's 8. Oh, and then when I multiply by the fourth root of another 2, that's the same as this. Put them all together. They have the same root. So that's just 2 times 2 times 2 times 2. Well, there's 4 2's there, 2 to the fourth. Just pull it out. That's equal to just 2. There's nothing left under the radical. That's it. That's my answer. Okay, when I have 2 to the fourth and I take the fourth root of something that has an exponent of 4, it just comes out. Okay, so 2 to the fourth, if I take the fourth root of it, that just comes out as 2. It's equal to this right here. Okay, 2. Hope that helps. What if you get a big number like this? What's the fifth root of that number? Oh boy, I have no idea. But let's find out what goes into this number. First of all, it's odd, so it's not divisible by 2. 2's are out. Add the digits. 5 plus 1 is 6. 6 plus 2 is 8. 8 plus 1 is 9. If the number that you get when you add up all the digits is divisible by 3, then the number is divisible by 3. So let's just start dividing by 3. Okay, divide by 3. 3 goes into 12 4 times, won't go into 1 at all. 3 goes into 15 5 times. Oh, 4 and 5, that's 9. Still divisible by 3. So let's do it again. Goes into 4 once, goes into 10 3 times with 1 remainder, 135. 5 and 3 is 8, plus 1 is 9, still divisible by 3. 3 goes into 13 4 times with 1 left over, 45. Now these are numbers I know. 3 goes into 45 15 times, and then I get a 5 left. 5 is a prime number. I can't divide it any further. Oh, look, that's 3 to the 1, 1, 2, 3, 4, 5. There's 5 threes there. That's 3 times 3 times 3 times 3 times 3 times 5. This is called the prime factorization of that number. Hopefully you've done that in another math class. But as soon as I say take the fifth root of this, there's 5 of these. It just comes out as a 3. These all come out like that. And what's left is the fifth root of 5. Done. That's my answer. That's as simple as I can make it. Okay. Hope that some of those examples help you with this. That's a start on properties of exponents and properties of roots.